70,000 years ago, while our ancestors were chipping flint tools on the African savanna and Neanderthals were sheltering in the limestone caves of Europe, something passed through the outermost boundary of our solar system. It was not a comet, it was not an asteroid, it was a star, an entire star, accompanied by a dim, veiled companion, drifted through the frozen halo of icy debris that marks the edge of our sun's gravitational domain. It came within 52,000 astronomical units of our sun. That is less than 1 light year, closer than any star has come in millions of years. And until 2015, no one on Earth had any idea it had happened. The star is called Scholz's star, named after the German astronomer Ralph Dieter Scholz, who first identified it in 2013, as a nearby but extraordinarily faint object lurking in the constellation Monoceros, near the plane of the Milky Way. It is a red dwarf, the smallest and dimmest class of star that still sustains hydrogen fusion. It has roughly 9% of the Sun's mass and emits so little light that even today, at a distance of about 22 light-years, it is invisible to the naked eye. Its apparent magnitude is 18.3, thousands of times too faint for human vision. It could have been sitting in our cosmic backyard for billions of years, and we would never have noticed it. And in a sense, that is exactly what happened. But Scholz's star is not alone. It travels with a companion, a brown dwarf, a body too massive to be a planet but too small to ignite sustained nuclear fusion. This companion has roughly 65 Jupiter masses and orbits its primary at a distance of about 0.8 astronomical units, roughly the distance from the Earth to the Sun. Together, this dim binary pair adds up to about 15% of the Sun's mass. Not much by stellar standards, but enough to carry gravitational influence, enough to tug on things as it passes. And pass it did. Through the Oort cloud, the vast, spherical shell of trillions of icy bodies that surrounds our solar system at distances ranging from 2,000 to 100,000 astronomical units from the Sun. The Oort cloud is the solar system's outermost frontier, a frozen archive of primordial material left over from the birth of the planets 4.6 billion years ago. It is the reservoir from which long-period comets are drawn, the source of the icy wanderers that occasionally plunge into the inner solar system, sprouting tails of gas and dust as they swing around the Sun before retreating back into the darkness. Scholz's star passed through this reservoir. It grazed the edge of our solar system, and it may have nudged some of those icy bodies in the process, setting in motion trajectories that will not reach the inner solar system for another 2 million years. This is not a hypothetical scenario. This is not a computer simulation of what might happen in the distant future. This already happened. It happened while humans were alive, while our species was learning to speak, to paint on cave walls, to navigate by the stars. An alien sun crept through our solar system's outermost boundary, and no one looked up. By the end of tonight, you are going to understand how a star can enter our solar system without anyone noticing, what it might have done to the trillions of icy bodies it passed through, why this discovery rewrites our understanding of how stable and isolated our solar system really is, and what it means that the next stellar intruder, one far more massive and far more disruptive, is already on its way. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The designation Scholz's star sounds modest, almost domestic, but the reality it represents is anything but modest. A binary stellar system, carrying roughly 15% of the Sun's mass, passed close enough to our solar system that it penetrated the Oort cloud, the outermost shell of icy debris that defines the gravitational boundary of our Sun's domain. To appreciate what this means, consider the scale involved. The Oort cloud extends from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. The outer edge of the Oort cloud, therefore, is roughly 15 trillion kilometers from us, and Scholz's star passed through it at a distance of approximately 52,000 astronomical units, or about 7.8 trillion kilometers from the Sun. That is close. In astronomical terms, that is extraordinarily close. It is less than 1 light-year, roughly 0.82 of a light-year. The nearest star to us today, Proxima Centauri, is 4.2 light-years away. Scholz's star came 5 times closer than our current nearest neighbour. The passage lasted thousands of years. The gravitational effects are still unfolding. And the discovery of this encounter was not the result of a deliberate search, but of a chance observation, a lucky coincidence in the vast ocean of astronomical data that we generate every day. If Ralph Dieter Scholz had not been looking in exactly the right way at exactly the right data, we might never have known. The star would have receded into the distance, its passage unmarked, its gravitational fingerprints slowly revealing themselves in the orbits of comets that no living human would ever connect to their cores. Now, let us begin. To understand how a star can enter our solar system, we first need to understand what the solar system actually is. Not the tidy diagram from a textbook, with 8 planets orbiting in neat concentric circles. The real solar system. The one that extends far, far beyond the last planet, far beyond the Kuiper belt, far beyond anything we have ever directly observed with a telescope or visited with a spacecraft. The real solar system is unimaginably vast, and its true boundary is defined not by the orbits of planets, but by the reach of the sun's gravity. The sun's gravitational influence extends outward in all directions, growing weaker with distance, but never quite reaching zero. At some point, roughly 100,000 astronomical units from the sun, the sun's gravity becomes so feeble that the gravitational pull of the Milky Way galaxy itself begins to dominate. This is the approximate outer edge of the sun's Hill sphere, the region within which the sun can hold objects in orbit. Beyond this boundary, you are in interstellar space, subject to the gravitational tides of the galaxy. Within it, you are part of the solar system, and this boundary is enormous. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers, or 93 million miles. 100,000 astronomical units is therefore 15 trillion kilometers. To put this in perspective, Pluto orbits the Sun at an average distance of about 39.5 astronomical units. The Voyager 1 spacecraft, launched in 1977, and currently the most distant human-made object, is at roughly 165 astronomical units from the Sun as of 2026. At its current speed of roughly 17 kilometers per second, Voyager 1 will not reach the inner edge of the Oort cloud for another 300 years, and it will take approximately 30,000 years to pass through the Oort cloud and exit the other side. 30,000 years. That is roughly the amount of time that has passed since the last Neanderthals walked the Earth. Voyager would need that entire span of history to cross the Oort cloud. That is how large our solar system truly is. Now let us build a scaled model to make this tangible. Imagine the Sun is a basketball, roughly 24 centimeters in diameter. On this scale, the Earth would be a small peppercorn about 26 meters away. Jupiter would be a cherry roughly 135 meters from the basketball. Pluto, at its average distance, would be a tiny grain of sand about 1 kilometer away. 1 kilometer. Already the model has stretched beyond a comfortable walking distance. But the Oort cloud, on this same scale, would not begin until you were roughly 26 kilometers from the basketball, and its outer edge would be at about 130 kilometers. The solar system, on this scale, would be a sphere roughly 260 kilometers in diameter, with the basketball sun at its center and a vast, diffuse shell of icy dust motes at its edges. Within that shell, the Oort cloud, lies a population of objects that is staggering in number and profound in significance. Astronomers estimate that the Oort cloud contains between several hundred billion and perhaps 2 trillion icy bodies larger than 1 kilometer in diameter. 2 trillion objects, each one a frozen remnant of the solar system's formation, a dirty snowball of water ice, methane, ammonia, and dust, orbiting the Sun at distances so great that a single orbit takes millions of years to complete. The total mass of the Oort cloud is estimated at roughly 5 to 40 Earth masses, though the uncertainty is large because we have never directly observed it. No telescope has ever imaged an Oort cloud object in situ. No spacecraft has ever visited one. The Oort cloud's existence is inferred entirely from the comets that occasionally fall out of it and into the inner solar system. providing brief, spectacular evidence of a vast unseen reservoir beyond the reach of our instruments. The Dutch astronomer Jan Hendrik Oort first proposed the existence of this cloud in 1950. He noticed something puzzling about long-period comets, those with orbital periods of thousands or even millions of years. These comets appeared to come from all directions in the sky, not just from the plane of the solar system where the planets orbit. This suggested they originated from a spherical distribution, not a flat disk. Oort also realized that comets are inherently fragile. Each pass through the inner solar system strips away material, shortening the comet's lifespan. A comet that has been orbiting for billions of years should have been destroyed long ago if its orbit regularly brought it close to the Sun. Therefore, there must be a distant reservoir constantly replenishing the supply, sending fresh comets inward for the first time. The Oort cloud was his answer. The cloud has two distinct regions. The outer Oort cloud, extending from roughly 20,000 to 100,000 astronomical units, is a sparse, spherical shell. Objects here are loosely bound to the Sun. Their orbits are easily disturbed by the gravitational tides of the Milky Way galaxy and by the gravitational pull of passing stars. A slight nudge, barely measurable by any instrument, can be enough to alter an Oort cloud object's orbit, just enough to send it on a long, slow fall toward the inner solar system. 2 million years later, it arrives near the Sun, sprouts a tail, and becomes what we call a comet. The inner Oort cloud, sometimes called the Hills cloud, after the astronomer Jack Hills, who proposed it in 1981, extends from roughly 2,000 to 20,000 astronomical units. This region is denser, with more objects packed into a tighter space, and its shape is thought to be more disk-like than spherical. Objects here are more tightly bound to the Sun and less easily perturbed, but they can still be dislodged by sufficiently close or massive stellar encounters. And they serve as a reservoir for the outer cloud, slowly feeding objects outward to replace those lost to interstellar space or to inward migration. This is the environment through which Scholz's star passed 70,000 years ago. It entered the outer Oort cloud, passed through at a distance of roughly 52,000 astronomical units from the Sun, and exited on the other side. At that distance, it was well within the outer cloud, but safely beyond the denser inner cloud. Its passage was fast, relatively speaking. Its velocity relative to the Sun was approximately 83 kilometers per second. At that speed, it would have crossed the relevant portion of the Oort cloud in a matter of thousands of years, perhaps less. A brief visit by astronomical standards, a blink of a cosmic eye, but even a brief visit by a star carries gravitational consequences. The question is not whether Scholz's star affected the Oort cloud. The question is how much. To understand the gravitational mechanics of a stellar flyby, consider a simple analogy. Imagine a pond covered with lily pads, floating freely on the surface. Now imagine someone walks slowly along the edge of the pond, dragging their hand through the water. The ripples from their passage push some lily pads gently outward. Most of them barely move. A few, those closest to the hand, are pushed harder. They might drift to a new position, or even be swept entirely off the pond. The hand does not need to touch every lily pad to affect them. It only needs to disturb the water they float on. Scholz's star was the hand, the Oort cloud was the pond, and the trillions of icy bodies within it were the lily pads. The star's gravity, even at 52,000 astronomical units from the Sun, was enough to subtly alter the trajectories of some Oort cloud objects. Not dramatically, not catastrophically, but measurably over time. Some objects that were on stable, circular orbits may have been nudged onto slightly more elongated paths. Some of those elongated paths may eventually bring them into the inner solar system, millions of years from now. The effects are slow, subtle, and cumulative. The implications of the Oort cloud's structure for planetary defense and cosmic history are profound. Every long-period comet we have ever observed, from the great comets of antiquity to the modern spectacles like Comet Hale-Bopp in 1997 and Comet Neowise in 2020, originated in this vast distant reservoir. They were dislodged from their ancient orbits by some combination of galactic tides, the gravitational pull of passing stars, and the subtle perturbations of giant molecular clouds in interstellar space. They fell inward for millions of years, accelerating imperceptibly, until they reached the inner solar system and began to outgas, forming the spectacular tails that make comets among the most visually striking objects in the night sky. But comets are also among the most dangerous. A long-period comet approaching the inner solar system for the first time is a high-velocity intruder with an orbit that is extremely difficult to predict accurately. Unlike asteroids, which typically orbit in the plane of the solar system and can be tracked for years or decades before a potential impact, long-period comets arrive from all directions, at high speeds, and with very little advance warning. A comet from the Oort cloud might not be detected until it is only a few years from Earth, far too late for any deflection mission. This is the class of impactors that planetary defense scientists fear most, because it is the class we are least prepared for. The Oort cloud, then, is not merely a scientific curiosity. It is a reservoir of potential danger, a storehouse of icy projectiles that can be launched toward the inner solar system by the slightest gravitational disturbance. And disturbances come regularly. Stars pass through the outer cloud roughly once every 50,000 to 100,000 years. Galactic tides continuously reshape the orbits of objects at the cloud's outer edge. Giant molecular clouds, dense concentrations of gas and dust that the Sun occasionally passes near, exert their own gravitational influence. The Oort cloud is under constant siege, and the comets it releases are the casualties of a slow, grinding war between the Sun's gravity and the galaxies. Now imagine the Oort cloud as a vast, spherical snow globe, with the Sun at its center and trillions of snowflakes drifting in slow, stately orbits at the globe's edges. The snowflakes are stable as long as no one disturbs the globe, but every 100,000 years or so, someone gives it a gentle tap. Most of the snowflakes barely move, a few drift inward, and one or two, given enough time, spiral all the way down to the center. That is the process by which comets are born, and Scholz's star was one of those taps. If you were to drive a car at highway speed, say 100 kilometers per hour, from Earth toward the inner edge of the Oort cloud, the journey would take roughly 2,300 years. To reach the outer edge, at 100,000 astronomical units, the drive would take roughly 170,000 years. And to reach Scholz's star at its closest approach distance of 52,000 astronomical units, you would be driving for roughly 89,000 years. These durations exceed the entire span of recorded human history by orders of magnitude. The distances involved are so vast that they make the interplanetary distances within the solar system distances that have challenged our engineering capabilities for decades look trivial by comparison. The WISE telescope that ultimately led to the discovery of Scholz's star was itself a remarkable instrument. Launched in December of 2009, the Wide Field Infrared Survey Explorer scanned the entire sky in 4 infrared wavelength bands, detecting objects that are too cool or too faint to be seen in visible light. Over the course of its primary mission, WISE catalogued over 747 million objects, including stars, galaxies, asteroids, and comets. Among these millions of objects buried in the data was a faint infrared source in the constellation Monoceros that would turn out to be the closest known stellar intruder in the history of our solar system. The process by which stars move through the galaxy is itself worth understanding. Stars do not orbit the galactic center in neat, circular paths. They follow complex, three-dimensional trajectories influenced by the combined gravitational pull of the galaxy's disk, its central bulge, and its dark matter halo. These trajectories can be thought of as slowly precessing ellipses, with each star bobbing up and down through the galactic plane and drifting inward and outward over timescales of hundreds of millions of years. As stars follow these orbits, they inevitably pass near other stars. Most of these passages are distant and inconsequential, but occasionally, 2 stars pass close enough that their mutual gravitational influence has measurable effects. The Sun's own motion through the galaxy carries it at roughly 220 kilometers per second around the galactic center. But this is not a smooth, uninterrupted journey. The Sun also has a peculiar velocity, a motion relative to the local standard of rest, the average velocity of nearby stars. This peculiar velocity is roughly 20 kilometers per second. directed roughly toward the constellation Hercules. This motion carries the Sun through different regions of the galaxy over time, bringing it into proximity with different groups of stars. The Sun's trajectory through the galaxy is the ultimate context for understanding stellar encounters like the Scholz's star flyby. Every such encounter is a consequence of the Sun's ongoing journey through a crowded, dynamic galaxy. The idea that comets could pose a threat to Earth is not new. Throughout history, comets have been regarded with a mixture of fascination and dread. Ancient civilizations from China to Rome to Mesoamerica recorded cometary appearances and often interpreted them as omens of disaster. The scientific understanding of comets as physical objects, icy bodies orbiting the Sun, began to develop only in the 17th and 18th centuries, with the work of Edmund Halley, who demonstrated that the comet that bears his name returns periodically, and Pierre-Simon Laplace, who developed the mathematical framework for understanding cometary orbits. The modern understanding of the Oort cloud adds a new dimension to the ancient fear of comets. It tells us that the source of comets is not some fixed, finite reservoir that will eventually be exhausted. It is a vast, continuously replenished storehouse, constantly stirred by external forces, capable of sending new comets inward for billions of years to come. The solar system will never run out of comets. As long as the Oort cloud exists, and as long as stars continue to pass nearby, fresh comets will continue to arrive in the inner solar system. Some of them will be spectacular, some of them will be dangerous, and all of them will be reminders that the solar system is not a closed system, but an open one, connected to the galaxy by bridges of gravity and time. And it gets stranger, because Scholz's star is not a single object. It is a binary system. The primary red dwarf and its brown dwarf companion orbit each other at a distance of roughly 0.8 astronomical units, completing one orbit every 4 years or so. During the flyby, both components exerted gravitational influence on the Oort cloud. The combined mass of the system, about 15% of the Sun's mass, was modest by stellar standards, but the binary nature of the system may have created additional gravitational complexity, subtle torques and perturbations that a single star of the same mass would not produce. There is another way to grasp the scale of the Oort cloud that connects it to human experience. Imagine you are standing in the center of a large city, say London. The Sun is beneath your feet. The Earth is 1 centimeter away, approximately the width of a fingernail. Mars is about 1.5 centimeters away. Jupiter is roughly 5 centimeters from you. Neptune, the outermost planet, is at about 30 centimeters, roughly a foot. At this scale, the inner edge of the Oort cloud begins at approximately 600 meters away, or about 6 city blocks. The outer edge of the cloud is at roughly 30 kilometers, well outside the city limits, out in the countryside beyond the suburbs. Scholz's star passed at approximately 16 kilometers from where you are standing, somewhere in the outskirts, threading through the sparse, invisible shell of frozen objects that mark the Sun's gravitational frontier. The objects within the Oort cloud are not packed tightly. Despite the trillions of bodies it contains, the cloud is almost entirely empty space. The average distance between neighboring Oort cloud objects in the outer cloud is estimated to be a significant fraction of an astronomical unit, perhaps tens of millions of kilometers. If you were floating in the outer Oort cloud and looked around, you would see nothing. No sun, or rather, the Sun would appear as just another bright star among many indistinguishable from its neighbors, except perhaps for a slight excess of brightness. No planets would be visible. No other Oort cloud objects would be detectable. You would be floating in what appears to be empty interstellar space, unaware that you are technically still within the solar system. The isolation would be total. This extreme sparseness is why the gravitational perturbation from Scholz's star was modest despite its passage through the cloud. Even though the star passed through a region theoretically populated by trillions of objects, those objects are so widely separated that only a tiny fraction of them experienced a gravitational perturbation strong enough to measurably alter their orbits. It is as if someone threw a pebble into the ocean. The ripples are real, but they affect only a vanishingly small fraction of the ocean's total volume. The origin of the name Oort cloud itself tells a story about how scientific ideas develop. the Estonian astronomer Ernst Öpik first proposed the existence of a distant cometary reservoir in 1932. He suggested that long-period comets must originate from a cloud of icy bodies at the edge of the solar system. Because their orbits are too elongated and too fragile to be primordial, they must be continuously replenished from some external source. Öpik's idea was ahead of its time and received little attention. It was not until 1950 that the Dutch astronomer Jan Hendrik Oort independently reached the same conclusion, using a more rigorous analysis of the original orbits of 19 comets. Oort showed that 10 of these comets had orbits consistent with arriving from a distance of roughly 40,000 to 50,000 astronomical units, and argued that a vast reservoir must exist at that distance. The scientific community accepted Oort's argument, and the cloud was named in his honour. Öpik's earlier contribution is acknowledged in the name sometimes used for the structure, the Öpik-Oort cloud. How do we know all of this? How can we be certain that a star passed through our solar system 70,000 years ago? The answer lies in the remarkable power of modern astrometry, the science of measuring the precise positions and motions of stars. And it begins with a discovery that almost did not happen. In 2013, the German astronomer Ralf-Dieter Scholz was studying data from NASA's Wide Field Infrared Survey Explorer, or WISE, a space telescope that surveyed the entire sky in infrared light between 2010 and 2011. Scholz noticed a faint object, catalogued as WISE J07-2003.20-084651.2, that had unusually low apparent motion across the sky. For a star so close to the Sun, about 22 light-years away, this was odd. Nearby stars typically show significant proper motion, a measurable drift across the sky, caused by their actual motion through space. A star at 22 light-years should be moving noticeably against the background of more distant stars. But this one was barely moving at all. The reason, as astronomer Eric Mamajek of the University of Rochester and his collaborators realized in 2015, was geometry. Scholz's star was not moving across our line of sight. It was moving almost directly away from us. Its velocity was overwhelmingly radial, directed outward along our line of sight, with very little tangential component. This made it nearly invisible in proper motion surveys, which detect sideways movement. It was like watching a car drive directly away from you on a straight highway. It does not appear to move left or right. It just gets smaller. This radial trajectory was the key to the discovery. If the star was moving almost directly away from the Sun, then at some point in the past, it must have been much closer. Mamajek and his team measured the star's current distance, roughly 22 light-years, and its radial velocity, roughly 83 kilometers per second outward. They then ran 10,000 simulations of the star's past trajectory, accounting for uncertainties in its position, distance, and velocity, as well as the gravitational influence of the Sun and the galaxy. 98% of those simulations showed Scholz's star passing through the Oort cloud. The median closest approach distance was approximately 52,000 astronomical units, or about 0.8 light-years, roughly 70,000 years ago. In less than 15 minutes after beginning the analysis, Mamajek later recounted, his team realized that this star had passed within a light-year of the solar system. It was at that time the closest known stellar flyby in the history of our solar system, and it had happened so recently, in astronomical terms, that the comets it may have disturbed are still on their way toward us. The discovery that Scholz's star had passed through the Oort cloud was published in the astrophysical journal Letters in February of 2015. The paper, authored by Eric Mamajek and 7 collaborators, was titled "The Closest Known Flyby of a Star to the Solar System." It was a measured, careful piece of scientific work, but its implications were profound, and they rippled through the astronomical community with a force that surprised even the authors. The central finding was straightforward. A binary stellar system, consisting of a dim red dwarf and an even dimmer brown dwarf, had passed within approximately 52,000 astronomical units of the Sun about 70,000 years ago. This was closer than any other known stellar encounter. The previous record holder for closest known approach was the star HIP 85605, but subsequent analysis revealed that its astrometric data was unreliable, leaving Scholz's star as the undisputed champion. At 52,000 astronomical units, the star had penetrated the outer Oort cloud, the vast reservoir of trillions of icy bodies that marks the outermost boundary of our solar system. But here is the problem. A star passing through the Oort cloud is not simply a curiosity. It is a potential trigger for cometary showers. The Oort cloud is a gravitationally delicate structure. Its objects orbit the Sun at distances so great that the Sun's gravity is extraordinarily weak. At 50,000 astronomical units, the Sun's gravitational acceleration is roughly 2.5 billion times weaker than it is at Earth's distance. An Oort cloud object at that distance takes approximately 11 million years to complete a single orbit. These objects are barely bound to the Sun. A passing star does not need to carry enormous mass or pass incredibly close to dislodge them. It merely needs to provide a gentle gravitational nudge, changing their velocity by a few meters per second, to alter their orbits sufficiently to send them on new trajectories. Some of those new trajectories will be outward, ejecting objects from the solar system entirely. These comets will drift into interstellar space, becoming part of the vast population of rogue icy bodies that wander between the stars. Others will have trajectories directed inward, toward the Sun and the planets. These are the ones that concern us, because an inward-directed Oort cloud object, given enough time, will eventually reach the inner solar system. And when it does, it becomes a comet, a potentially dangerous comet. The timescale for this process is long, very long. An object nudged from the outer Oort cloud onto an inward trajectory does not arrive at the inner solar system immediately. It falls slowly, pulled by the Sun's feeble gravity across tens of thousands of astronomical units. The journey takes roughly 2 million years. 2 million years from the moment of the gravitational perturbation to the moment the object crosses the orbit of Neptune. After that, the object enters the realm of the giant planets, where additional gravitational interactions can further modify its orbit, sending it deeper into the inner solar system or ejecting it entirely. This means that if Scholz's star perturbed Oort cloud objects 70,000 years ago, the first of those objects will not arrive in the inner solar system for approximately another 1.9 million years. We are not in immediate danger, but the perturbation has already occurred. The objects are already on their way. The clock is already ticking. It is just a very, very slow clock. The mechanics of how a stellar flyby perturbs the Oort cloud can be understood through a concept called the impulse approximation. When a star passes through the cloud, it spends a relatively short time, perhaps a few thousand years, within the cloud's boundaries. During this transit, each Oort cloud object experiences a gravitational tug from the passing star. The strength and direction of this tug depend on the object's distance from the star and its position relative to the star's trajectory. Objects close to the star receive a strong tug. Objects far from the star receive a weak one, and the direction of the tug changes as the star moves past, creating a complex pattern of velocity changes across the cloud. The net effect is a velocity change, called a velocity impulse, that is largest for objects near the point of closest approach and falls off roughly as the inverse of the distance from the star's trajectory. For Scholz's star, with its mass of roughly 0.15 solar masses and its velocity of 83 kilometers per second, the velocity impulse for an Oort cloud object at the point of closest approach was of the order of a few tens of meters per second. That may sound small, but for an object that is barely gravitationally bound to the Sun, an object whose own orbital velocity at 50,000 astronomical units is only about 130 meters per second, a change of a few tens of meters per second is significant. It is enough to change the shape, size, and orientation of the object's orbit. It is enough in some cases to unbind the object from the Sun entirely, sending it drifting off into interstellar space. And it is enough, in other cases, to send the object falling inward on a trajectory that will carry it past the planets and into the inner solar system over the next few million years. The gravitational interaction between a passing star and the Oort cloud is not the only external force shaping the cloud structure. The galactic tide, The differential gravitational pull of the Milky Way's disk on objects at different distances from the Sun plays an equally important role. The galactic tide operates continuously, not episodically like stellar encounters. It slowly torques the orbits of Oort cloud objects, rotating their orbital planes and changing their eccentricities over timescales of millions of years. The interplay between the galactic tide and stellar encounters creates the cloud's observed structure, a spherical outer shell, continuously stirred by both forces, and a flatter, denser inner structure that is more resistant to external perturbation. Giant molecular clouds, the dense regions of interstellar gas and dust from which stars form, also play a role. These clouds can have masses of hundreds of thousands of solar masses and sizes of tens of parsecs. When the Sun passes near or through a giant molecular cloud, the cloud's gravity can produce perturbations comparable to a closed stellar encounter. The Sun encounters a giant molecular cloud roughly once every 300 million to 500 million years, and each encounter can produce a significant perturbation of the Oort cloud. Some researchers have speculated that passages through giant molecular clouds may be responsible for the most intense cometary showers in the geological record, those that may correlate with mass extinction events. But the evidence remains circumstantial, and the hypothesis is not yet confirmed. The long-period comets that arrive in the inner solar system from the Oort cloud are, in a sense, messengers. Each one carries information about the environment from which it was dislodged. Its chemical composition reflects the conditions in the protoplanetary disk where it formed. Its orbital parameters reflect the perturbation that sent it inward, whether from a passing star, the galactic tide, or a giant molecular cloud. And the timing of its arrival, millions of years after the initial perturbation, provides a kind of cosmic clock, linking past events to present observations. The prospect that Scholz's star perturbed objects that will become visible comets in the distant future is tantalizing. It means that, in approximately 2 million years, astronomers may be able to observe comets whose orbits bear the gravitational signature of the 2015 flyby. They will be able to trace these comets back to the constellation Gemini, to the direction from which Scholz's star approached, and to confirm, with direct observation, what we currently know only from mathematical reconstruction. We will not be there to see it, but the comets will come regardless. And the story they tell will be the story of a dim star that passed too close long ago, in the time before written history, before cities, before agriculture, before everything we call civilization. The story of Scholz's star is, ultimately, the story of the cosmos writing its own history in the language of orbits and gravity, a language that we have only recently learned to read. The 2018 study by Carlos and Raúl de la Fuente Marcos of the Complutense University of Madrid, along with Sver Arseth of the University of Cambridge, provided the first observational evidence supporting the Scholz's star flyby hypothesis. The researchers analyzed the orbits of nearly 340 objects in the solar system that follow hyperbolic trajectories. Hyperbolic orbits are V-shaped, open-ended paths that indicate an object is not gravitationally bound to the Sun. These objects are either passing through the solar system from interstellar space or have been ejected from the Oort cloud by some external perturbation. The key finding was this: if these hyperbolic objects were randomly distributed, meaning they originated from all directions equally, their radiance, the points in the sky from which they appear to originate, should be evenly scattered across the celestial sphere. But that is not what the researchers found. Instead, they discovered a statistically significant cluster of radiance, pointing toward the constellation Gemini. 36 objects had trajectories that traced back to the same general direction. This overdensity was consistent with a gravitational disturbance originating from the direction of Scholz's star's closest approach. The constellation Gemini is precisely where you would expect to find such a signal if a star had passed through the Oort cloud from that direction and nudged objects inward. The timing and location matched. The direction of the radiant cluster coincided with the predicted position of Scholz's star during its perihelion passage 70,000 years ago. The researchers concluded that the close encounter with Scholz's star provides a plausible explanation for the observed clustering. Carlos de la Fuente Marcos noted that the detected sample represents only those objects that passed relatively close to Earth. The total number of objects perturbed by the flyby could have been significantly higher. This finding was not universally accepted without debate. Some researchers, including Wesley Fraser of Queen's University Belfast, pointed out that the dataset of hyperbolic objects suffers from observational biases. Many of these objects were only briefly observed, and the precision of their orbital data is limited. It is possible that the apparent clustering is partly or entirely an artifact of how and where we look for these objects, rather than a genuine signal from a stellar flyby. The scientific method demands caution, and the debate continues. But Mamajek himself, while acknowledging the uncertainties, emphasized a broader point. Scholz's star is probably not the only star to have passed through the Oort cloud. Over the history of the solar system, spanning 4.6 billion years, many stars have come close enough to disturb our cometary reservoir. About 10 stars are estimated to pass through the Oort cloud every million years. Most of them are small, fast, and distant enough that their gravitational effect is negligible. But occasionally, a more massive or slower-moving star passes close enough to cause a significant perturbation. And these perturbations, accumulated over billions of years, have shaped the Oort cloud into the structure we observe today. There is a way to visualize this that makes the scale visceral. If you could watch a time-lapse of the solar system from above, compressed so that 1 year of real time passes in 1 second of viewing time, you would need to watch for roughly 22 hours before Scholz's star completed its passage through the Oort cloud. But you would need to watch for roughly 23 days before the first perturbed comets reached the orbit of Neptune, and you would need to watch for roughly 63 days before those comets reached the inner solar system. The entire process, from the star's arrival in the cloud to the comet's arrival near Earth, unfolds over a timescale that even in this accelerated view spans weeks of continuous watching. The cosmos operates on timescales that are not just longer than human life, but longer than human civilization, longer than human speciation, longer than the entire Pleistocene epoch during which modern humans evolved. The radial velocity of Scholz's star, roughly 83 kilometers per second, is worth placing in context. This is fast by human standards, roughly 300,000 kilometers per hour, about 250 times faster than a rifle bullet and roughly 25 times faster than the fastest spacecraft humanity has ever launched. But by stellar standards, it is not unusual. Stars in the solar neighborhood have velocities ranging from a few kilometers per second to well over 100 kilometers per second relative to the local standard of rest. The Sun itself moves at about 20 kilometers per second relative to its neighbors. Scholz's star's high velocity relative to the Sun is partly a consequence of its age and its orbital history within the galaxy. Older stars tend to have higher random velocities because they have had more time to be accelerated by gravitational encounters with giant molecular clouds and spiral arms. The speed of the flyby matters because it determines the duration of the gravitational perturbation. A slow-moving star, one traveling at only 10 or 20 kilometers per second relative to the Sun, would spend much longer within the Oort cloud and would exert a correspondingly stronger perturbation. This is why Gliese 710, despite being only about 4 times more massive than the Scholz's star system, will produce a perturbation roughly 20 times stronger. Gliese 710 is moving at approximately 14.5 kilometers per second, about 1/6 of Scholz's star's velocity. This slower speed means it will linger in the Oort cloud much longer, giving its gravity more time to act on each Oort cloud object. The gravitational encounter parameter, sometimes called gamma, captures this relationship precisely. It is defined as the mass of the passing star divided by the product of its velocity and its closest approach distance. A high gamma means a strong perturbation. Scholz's star had a relatively low gamma because its high velocity partially compensated for its moderately close approach. Gliese 710 will have a gamma approximately 20 times higher, making it the most disruptive known stellar encounter in the past and future of the solar system. And it gets worse, because the flyby of Scholz's star while the closest documented stellar encounter was relatively mild. The star's mass was low, its velocity was high, and it passed through the low-density outer reaches of the cloud. It was, in the language of gravitational dynamics, a weak perturbation. The parameter that quantifies the strength of a stellar flyby, sometimes designated gamma, is calculated as the mass of the passing star divided by the product of its velocity and closest approach distance. For Scholz's star, this parameter was low. The perturbation was real but modest. But not all stellar encounters are modest. Some are devastating. And the most devastating one we know of is not in the past. It is in the future. In approximately 1.29 million years, a star called Gliese 710 will pass through the inner Oort cloud at a distance of roughly 10,500 astronomical units from the Sun. That is 5 times closer than Scholz's star came. And Gliese 710 is a significantly more massive star, an orange dwarf with roughly 60% of the Sun's mass, or about 4 times the mass of the Scholz's star system. Its gamma parameter, the measure of encounter strength, is estimated to be 20 times higher than any other known stellar flyby in the past or future history of the solar system. Gliese 710 will not merely graze the outer Oort cloud, it will plunge deep into it, passing through the denser inner regions where far more objects reside. Computer simulations predict that this encounter will trigger an observable cometary shower lasting 3 to 4 million years, with an average density of approximately 10 comets per year entering the inner solar system. The number of Oort cloud objects deflected into Earth-crossing orbits will increase by roughly 25 to 50% compared to the baseline rate. The comets will arrive from a concentration near the anti-perihelion direction of the star's passage, then gradually spread across the sky as the shower evolves. The mathematical framework for understanding the effects of a stellar flyby on the Oort cloud draws on the theory of gravitational perturbations developed over centuries by astronomers from Newton to Laplace to modern computational dynamicists. The key insight is that a passing star does not need to capture or directly deflect Oort cloud objects. It merely needs to change their velocities by a small amount. Even a velocity change of a few centimeters per second, applied to an object on a barely bound orbit at 50,000 astronomical units from the Sun, can be enough to push that object onto a new trajectory. Some of these new trajectories will be directed inward toward the Sun. Others will be directed outward into interstellar space. The balance between inward and outward deflection depends on the geometry of the encounter, the mass and velocity of the passing star, and the initial conditions of the Oort cloud objects. The concept of gravitational focusing adds another layer to this picture. As a star approaches the Sun, its trajectory is bent by the Sun's gravity. This bending acts like a lens, focusing the star's gravitational influence on the Oort cloud objects that lie near the star's closest approach point. The result is that the perturbation is not uniformly distributed across the cloud, but is concentrated in a cone-shaped region surrounding the star's trajectory. This focusing effect enhances the perturbation for objects in the path of the flyby and diminishes it for objects far from the path. The 2018 study's finding of a radiant cluster in Gemini is consistent with this focused perturbation because the cluster points back along the direction from which Scholz's star approached. The discovery also raises a profound question about what we would do if we discovered a star on a more threatening trajectory. Scholz's star was detected only after its flyby. Its nearly radial recession velocity made it invisible to proper motion surveys until WISE detected its infrared signature. What if a similar star were approaching the Sun rather than receding from it? Current surveys might detect it years or decades before closest approach, depending on its brightness and trajectory. But detecting an approaching star and predicting its exact closest approach distance are two very different tasks. The uncertainties in stellar parallax, proper motion, and radial velocity measurements translate into large uncertainties in predicted flyby distance. A star predicted to pass at 100,000 astronomical units might actually pass at 50,000 or at 200,000. The difference matters enormously for the strength of the perturbation. Moreover, there is no mechanism for preventing or mitigating a stellar flyby. Unlike asteroid deflection, where we can at least conceive of kinetic impactors or nuclear devices to alter an object's trajectory, there is no technology that could alter the trajectory of a star. Stars are simply too massive, too distant, and moving too fast for any conceivable human intervention. A stellar flyby is a natural event that must simply be endured, its consequences accepted. The only preparation we can make is to catalogue the objects in the Oort cloud that might be perturbed, predict which ones might be deflected toward the inner solar system, and prepare to detect and deflect any that pose a direct threat to Earth. This is a humbling realization. We live in a solar system that is subject to forces we cannot control, on timescales we can barely comprehend, from sources we have only recently begun to catalogue. The cosmos is not hostile, but it is indifferent. And indifference, on a cosmic scale, is its own kind of danger. The story of how the research community reacted to the Scholz star discovery is itself instructive. When Mumajek's paper was published in 2015, it generated significant media attention. Headlines proclaimed that a star had invaded the solar system. The public response ranged from genuine fascination to mild alarm. Some people worried about imminent cometary impacts. Others dismissed the discovery as irrelevant because of the vast timescales involved. Both reactions missed the essential point. The significance of the Scholz star flyby is not that it poses an immediate danger. It does not. The significance is what it tells us about the dynamic nature of our cosmic environment. It demonstrates that stellar encounters are not hypothetical. They are historical facts. They have happened, they are happening, and they will continue to happen. The solar system is not a sealed chamber. It is an open room with an unlocked door, and visitors come and go on timescales that dwarf human awareness. The detection of Scholz's star also provided a valuable test case for the emerging field of stellar encounter prediction. Using data from the Hipparcos and Gaia space missions, astronomers have been building increasingly precise catalogues of stellar trajectories, identifying which stars will pass closest to the Sun in the coming millions of years. Scholz's star was, in a sense, a retroactive prediction, a flyby identified after the fact. But the techniques used to reconstruct its trajectory are the same ones being used to predict future encounters. And those predictions have identified one future encounter that stands out above all others. Gliese 710, an orange dwarf star, 60% of the Sun's mass, currently 62.3 light-years away, and approaching at roughly 14.5 kilometers per second. In approximately 1.29 million years, it will pass through the inner Oort cloud at a distance of roughly 10,500 astronomical units, 5 times closer than Scholz's star came. At its closest approach, it will shine in the night sky as a bright orange point of light. Magnitude -2.7 to -3.2, rivaling Jupiter in brilliance and unlike anything our species has ever seen in the heavens. If humanity endures for another million years, the approach of Gliese 710 will be one of the great spectacles of the deep future. It will grow brighter in the sky over the course of hundreds of thousands of years, a slow-motion cosmic event that unfolds over timescales that make human history look like a single heartbeat. And as it passes through the Oort cloud, its gravity will stir the icy bodies within, setting in motion a cometary cascade that will unfold over the subsequent millions of years. The contrast between Scholz's star and Gliese 710 encapsulates the range of stellar encounter scenarios. Scholz's star was small, fast, and passed through the outer cloud. Its effects were modest. Gliese 710 will be larger, slower, and will penetrate deep into the inner cloud. Its effects will be dramatic by comparison, and between these two extremes lies a spectrum of possible encounters, each one shaped by the unique combination of stellar mass, velocity, and closest approach distance. The solar system has experienced all of these scenarios many times over its 4.6 billion year history, and it will experience them many times more. But here is what makes this truly terrifying. Gliese 710 is already on its way. It is currently 62.3 light-years from the Sun, in the constellation Serpens. It has a visual magnitude of 9.69, too faint to see with the naked eye. But it is moving, it is approaching, and when it arrives, it will be the brightest object in the night sky apart from the Sun, Moon, and Venus. shining at an apparent magnitude of roughly -2.7 to -3.2. It will be visible to the naked eye as a bright, orange-tinted star, growing slowly brighter year after year over the course of tens of thousands of years as it approaches. Our distant descendants, if they are still here, will watch it grow in the sky and know what it means. Something is wrong with our assumptions about the isolation and stability of our solar system. We tend to think of the Sun and its planets as an island, a self-contained system drifting peacefully through the Milky Way, largely unaffected by the billions of other stars in the galaxy. But that picture is wrong. The Sun is not alone. It is moving through a galaxy containing an estimated 100 to 400 billion stars, many of which cross and recross each other's paths over timescales of millions of years. The galaxy is not a static field of fixed points. It is a dynamic, churning environment in which stars jostle and drift, occasionally passing close enough to disturb each other's planetary systems, cometary clouds, and potentially even the orbits of planets themselves. The average rate of stellar encounters close enough to enter the Oort cloud is estimated at roughly 1 every 50,000 to 100,000 years. Most of these encounters involve small, fast-moving stars that pass through the outer cloud with minimal effect. But once every few million years, a more massive or slower-moving star passes close enough to produce a significant perturbation. And once every 100 million years or so, an encounter strong enough to penetrate the inner Oort cloud and trigger a major cometary shower occurs. These timescales are long compared to human civilization, but they are short compared to the age of the solar system. Over 4.6 billion years, the Sun has experienced tens of thousands of Oort cloud grazing encounters, and hundreds of encounters strong enough to significantly perturb the cometary population. Some researchers have speculated that periodic cometary showers triggered by stellar encounters may correlate with mass extinction events in Earth's geological record, though this hypothesis remains controversial, and the evidence is far from conclusive. What is clear is that our solar system has never been truly isolated. It has always existed within a galactic environment, subject to the gravitational influences of passing stars, giant molecular clouds, and the tidal forces of the Milky Way's disk. The Oort cloud is the most visible manifestation of this interaction, a structure that was shaped by galactic forces and continues to be modified by them today. Scholz's star, far from being a unique event, was merely the latest in a long line of cosmic visitors, most of them unknown, most of them lost to the deep past. All of them remind us that the boundaries of our solar system are porous, and always have been. The discovery of Scholz's star's flyby opened several lines of scientific inquiry, each one probing a different aspect of our understanding of the solar system, stellar dynamics, and the nature of cosmic risk. Let us explore 5 of these threads in detail. The first thread concerns the question of how Scholz's star was missed for so long. This is a star that is only 22 light-years from the Sun. That puts it among the 100 closest stellar systems to our own. And yet it was not discovered until 2013, decades after most other nearby stars had been catalogued. How is this possible? The answer lies in a combination of factors that conspired to render Scholz's star nearly invisible. First, it is intrinsically very dim. As a red dwarf of spectral type M9, it sits at the very bottom of the main sequence, the boundary between stars that sustain hydrogen fusion and brown dwarfs that do not. Its luminosity is a tiny fraction of the Sun's, roughly 1/10,000th. At a distance of 22 light-years, this translates to an apparent visual magnitude of about 18.3, far too faint for any naked eye observation, and requiring a moderately large telescope to detect. Second, it lies near the galactic plane, in a region of the sky densely packed with background stars. This makes it easy to overlook in optical surveys, where it would appear as just another faint red point among millions. Third, and most critically, its proper motion is unusually low for a nearby star. Stars that are close to the Sun typically show significant apparent motion across the sky, making them stand out in surveys that compare images taken years apart. Scholz's star, because of its nearly radial trajectory away from the Sun, had almost no detectable sideways motion. It was hiding in plain sight, camouflaged by its dimness, its location, and its trajectory. It took the infrared sensitivity of NASA's WISE telescope to pick it out. WISE surveyed the entire sky in infrared wavelengths, where cool red objects shine relatively brighter than they do in visible light. Even so, Scholz's star was initially just one of billions of point sources in the WISE catalogue. It was Ralph Dieter Scholz's careful analysis of the data, specifically his search for nearby objects with low proper motion, that brought it to attention. The lesson here is sobering. If a star this close could remain undiscovered until 2013, how many other dim nearby objects have we missed? The answer, almost certainly, is many. Surveys like WISE and its successor, NEOWISE, have been highly successful at finding nearby brown dwarfs and low-mass stars. But the catalogue is not complete. There may be additional, dim objects within 20 or 30 light-years that have not yet been detected, including objects on trajectories that will bring them close to the Sun in the future. The European Space Agency's Gaia mission, which is creating the most precise three-dimensional map of the Milky Way ever assembled, will help close this gap. Gaia has measured the positions, distances, and motions of over 1 billion stars, enabling astronomers to identify not just which stars are close today, but which ones will be close in the future. The analysis of Gaia data has already identified several dozen stars that will pass within 2 parsecs of the Sun over the next 5 million years. But new discoveries continue to emerge as the data is processed and refined. The second thread concerns what Scholz's star actually did to the Oort cloud during its passage. The initial 2015 paper by Mamajek and collaborators was cautious on this point. They noted that Scholz's star's relatively high velocity, about 83 kilometers per second, and its relatively low mass, about 15% of the Sun's mass, meant that the gravitational perturbation was likely modest. Nathan Kaib, an expert on Oort cloud dynamics, confirmed in correspondence with Mamajek that the effect on long-period comet flux was unlikely to be significant. But the 2018 study by De La Fuente Marcos and colleagues suggested the effects might have been greater than initially thought. Their analysis of hyperbolic orbits pointed to a statistically significant signature of the flyby in the distribution of solar system objects. They also noted that their simulations suggested Scholz's star may have passed even closer than the 0.6 light-year lower limit established in the 2015 study. A later recalculation, using updated solar system data, placed the most likely perihelion distance at 0.33 parsecs, approximately 68,700 astronomical units, with the time of closest approach refined to approximately 79.9 thousand years ago, with 90% confidence intervals spanning 78.6 to 81.1 thousand years. The math is striking. At its closest approach, even with its modest mass, Scholz's star exerted a gravitational acceleration on nearby Oort cloud objects that, while tiny in absolute terms, was comparable to or greater than the Sun's own gravitational hold on those objects. For an Oort cloud body at 50,000 astronomical units, the Sun's gravitational acceleration is approximately 7 times 10 to the negative 9th meters per second squared. Scholz's star, passing at a comparable distance, would have exerted a gravitational pull of a similar order of magnitude. That is enough to perturb orbits. Not enough to rip objects away from the Sun, but enough to change the shape and orientation of their orbits, pushing some onto paths that will eventually bring them inward. The third thread involves the question of whether our ancestors could have seen Scholz's star during its passage. This is a fascinating intersection of astronomy and anthropology. 70,000 years ago, anatomically modern humans were present in Africa and beginning to migrate outward. Neanderthals occupied Europe and parts of Western Asia. Denisovans inhabited Eastern Asia. These were our relatives, our contemporaries, beings with large brains and complex behaviors who may well have spent long evenings gazing at the night sky. Even at its closest approach, Scholz's star would have been far too dim for the naked eye to detect under normal circumstances. At a distance of about 52,000 astronomical units, the system would have had an apparent magnitude of roughly 11.4. That is about 100 times too faint for unaided human vision, which can detect objects down to about magnitude 6 under ideal conditions. Our ancestors would not have seen it as a steady light in the sky. But red dwarfs are known for their flares. These are sudden, dramatic increases in brightness caused by magnetic reconnection events on the star's surface. A red dwarf flare can increase the star's brightness by factors of tens or even hundreds for minutes or hours at a time. If Scholz's star flared during its closest approach, it could have briefly brightened to a magnitude visible to the naked eye, appearing as a faint reddish, transient light in the constellation that was then in the position of its closest approach. It would have appeared, flickered, and vanished, perhaps over the course of a single night. A brief, mysterious light in the sky that would have had no explanation in the cosmology of our Stone Age ancestors. Did they see it? We will almost certainly never know. There are no written records from 70,000 years ago. No cave paintings have been identified that unambiguously depict a transient astronomical event from that era. But the possibility is haunting. The idea that a star passed through our solar system while our ancestors watched, unable to comprehend what they were seeing, is one of those moments where science and the human condition intersect in deeply moving ways. The fourth thread concerns the broader population of stellar flybys that the Sun has experienced over its 4.6 billion year history. Scholz's star was not the first star to enter the Oort cloud. It was merely the first one we identified with certainty. The Sun orbits the center of the Milky Way at a speed of roughly 220 kilometers per second, completing one full galactic orbit every 225 to 250 million years, a period sometimes called a galactic year. Over the course of one galactic orbit, the Sun passes through regions of varying stellar density, including the denser spiral arms of the galaxy, where stellar encounters are more frequent. Corinne Baylor-Jones of the European Space Agency used data from the Gaia mission to reconstruct the trajectories of 320,000 stars in the Milky Way, identifying those that have come or will come closest to the Sun over a 10 million year window. His findings, published in Astronomy and Astrophysics, showed that the average rate of stellar encounters within 2 parsecs of the Sun is roughly one every 50,000 years. 16 stars were identified that will pass within 2 parsecs over the next 5 million years. Of these, Gliese 710 stands out as by far the most significant. But Baylor-Jones also noted the limitations of the analysis. The trajectories of stars can only be projected accurately for a few million years into the past or future. Beyond that, uncertainties in position and velocity measurements compound, and the gravitational influence of other stars and galactic structures makes predictions unreliable. Over the 4.6 billion year history of the solar system, hundreds of thousands of stars have passed within the outer Oort cloud. Some of them were far more massive and far slower moving than Scholz's star. Some of them may have passed through the inner Oort cloud, or even close enough to perturb objects in the Kuiper belt. We will never know about most of them. They are lost to the deep past, their trajectories erased by the cumulative uncertainties of galactic dynamics. The discovery timeline of Scholz's star illustrates how quickly astronomical knowledge can advance when new instruments come online. The WISE telescope operated for only about 14 months in its primary cryogenic mission, from January 2010 to September 2010, before its hydrogen coolant was exhausted. A brief post-cryogenic mission called NEOWISE continued for several more months, and then the spacecraft was placed in hibernation. It was reactivated in late 2013 for a new mission focused on near-Earth objects. During those 14 months of primary operation, WISE surveyed the entire sky twice in 4 infrared wavelength bands, producing a catalogue of over 747 million objects. Scholz's star was among them, hidden in that vast dataset, waiting to be noticed. The process by which Mamajek and his team determined the flyby trajectory is a masterclass in astronomical detective work. They began with the WISE position and the ground-based radial velocity measurement. They then obtained proper motion measurements from multiple sources, including the 2-micron all-sky survey and the Southern African Large Telescope. These measurements were combined with the star's parallax distance to produce a 6-dimensional description of the star's current state, 3 spatial coordinates, and 3 velocity components. This 6-dimensional state vector was then integrated backward in time using a gravitational model that included the Sun, the Milky Way's disk, bulge and halo, and the gravitational influence of nearby massive objects. The integration was performed 10,000 times, each time with slightly different initial conditions drawn from the measurement uncertainties. The resulting ensemble of trajectories showed, with 98% confidence, that Scholz's star had passed through the Oort cloud roughly 70,000 years ago. The precision of this reconstruction depends critically on the accuracy of the input measurements. The parallax distance, in particular, is a key parameter. A small error in parallax translates to a large error in distance, which propagates into a large error in the reconstructed trajectory. For Scholz's star, the parallax was measured to be approximately 45.3 milliarcseconds, corresponding to a distance of roughly 22 light-years. The uncertainty in this measurement was about 1.7 milliarcseconds, or roughly 4%. This 4% uncertainty translates to an uncertainty of approximately 2,000 astronomical units in the closest approach distance, well within the Oort cloud's boundaries. The conclusion that Scholz's star passed through the Oort cloud is robust against plausible measurement errors. The radial velocity measurement is equally critical. If the star's velocity along our line of sight is measured incorrectly, the reconstructed trajectory will be wrong. For Scholz's star, the radial velocity was measured at approximately 83.1 kilometers per second, with an uncertainty of less than 1 kilometer per second. This high precision, obtained through spectroscopic observations with ground-based telescopes, was essential for constraining the trajectory. Future observations of Scholz's star, though it is now receding rapidly, could further refine the flyby parameters. Additional parallax measurements from Gaia, combined with improved proper motion data, will tighten the uncertainty ellipse around the closest approach distance and timing. These refinements may not change the fundamental conclusion that the star passed through the Oort cloud, but they will sharpen our understanding of exactly how close it came and exactly when it arrived. The astronomical community has also considered whether any other known stars could have had flybys comparable to Scholz's star within the last few 100,000 years. A comprehensive search using Gaia data, conducted by several independent research groups, has not identified any competitor. Scholz's star remains the closest known stellar flyby in the recent history of the solar system, but the search continues, and new candidates may emerge as Gaia's data is processed and updated. The fourth data release from Gaia, expected in the coming years, will provide improved astrometric solutions for millions of additional stars, potentially revealing previously unrecognized close encounters. The question of whether there are other undiscovered stellar intruders in the Sun's past is one of the most active areas of research in galactic dynamics. The Gaia space mission, with its precise measurements of over 1 billion stellar positions and velocities, is the primary tool for this investigation. By tracing stellar trajectories backward and forward in time, astronomers can identify which stars have come or will come closest to the Sun. But the precision of these predictions degrades rapidly beyond a few million years due to the cumulative effects of gravitational perturbations from other stars and the galaxy's overall structure. For encounters deeper in the past, say tens of millions or hundreds of millions of years ago, we are essentially blind. We know, statistically, that many close encounters must have occurred, but we cannot identify the specific stars responsible. This statistical knowledge is itself valuable. By combining the known rate of stellar encounters with models of Oort cloud dynamics, researchers can estimate the long-term average cometary flux from the cloud. This baseline flux is what we observe today, the steady trickle of long-period comets that arrive in the inner solar system at a rate of roughly 1 to 2 per year, bright enough to detect. Superimposed on this baseline are occasional spikes, cometary showers triggered by particularly close or massive stellar encounters. These showers last for a few million years each and can increase the cometary flux by factors of several. Over the 4.6 billion year history of the solar system, there have likely been dozens or hundreds of such showers. The possibility that some of these showers contributed to mass extinction events remains one of the most provocative hypotheses in planetary science. The extinction of the dinosaurs 66 million years ago was caused by an asteroid impact, not a comet. But other extinction events in the geological record do not have clearly identified causes. Could some of them have been triggered by cometary impacts during a stellar encounter-driven shower? The question is open, and the evidence is tantalizing but inconclusive. One intriguing piece of evidence comes from the study of microspherules and iridium anomalies in deep-sea sediments. These tiny particles, which form from the molten debris of cosmic impacts, can be dated and counted through geological strata. Some researchers have identified apparent periodicities in their abundance, with peaks occurring roughly every 26 to 30 million years. These periodicities have been linked, speculatively, to the Sun's oscillation through the galactic plane, which brings it closer to the denser midplane, where stellar encounters and giant molecular cloud passages are more frequent. But the statistical significance of these periodicities is debated, and alternative explanations, including observational biases and statistical noise, cannot be ruled out. What is clear is that the solar system exists within a galactic ecosystem, not apart from it. The stars that surround us are not static decorations. They are fellow travelers through the galaxy, each one following its own orbital path, each one carrying its own gravitational influence. And every so often, one of them passes close enough to remind us that our boundaries are not walls but suggestions, permeable membranes through which the galaxy's influence leaks in, slowly, patiently, inevitably. The binary nature of Scholz's star raises additional questions that have not been fully explored. When a binary system passes through the Oort cloud, the two components create a more complex gravitational field than a single star of equivalent total mass. The objects in the cloud experience not one gravitational tug, but two, from slightly different directions and at slightly different times. The interaction between these two tugs can create resonances and interference patterns in the velocity perturbations, potentially enhancing the effects in some regions of the cloud while cancelling them in others. This complexity makes the detailed modelling of the Scholz's star flyby more challenging than for a single star encounter. The brown dwarf companion, with its roughly 65 Jupiter masses, is itself an object of considerable interest. Brown dwarfs occupy a unique position in the hierarchy of cosmic objects. They are too massive to be planets, but too small to sustain the hydrogen fusion that powers true stars. They glow dimly in infrared light, heated by the gravitational contraction from their formation and by a brief period of deuterium fusion early in their lives. Over billions of years, they cool and fade, becoming increasingly difficult to detect. The brown dwarf companion to Scholz's star is classified as a T5 dwarf, a cool, methane-rich object with an effective temperature of roughly 1000 to 1200 Kelvin. It is far dimmer than its red dwarf primary and would have been virtually undetectable during the flyby, even with modern instruments placed at the distance of closest approach. The combined system, red dwarf and brown dwarf, orbiting each other once every 4 years at a distance of roughly 120 million kilometers, presents a gravitational signature that is both weaker than a single sun-like star and more complex in its structure. Understanding how this binary perturbation affected the Oort cloud in detail would require high-resolution numerical simulations that track the trajectories of millions of test particles as the binary system sweeps past. Such simulations have been performed in a general sense, but not at the resolution needed to make specific predictions about individual perturbed objects. The search for traces of Scholz's star's passage in the present-day solar system extends beyond the study of hyperbolic orbits. Some researchers have looked for signatures in the distribution of long-period comets currently approaching the inner solar system. If Scholz's star perturbed a significant number of Oort cloud objects, and if some fraction of those objects were already on relatively short-period orbits within the inner Oort cloud, then a few of them might have arrived in the inner solar system within the last few tens of thousands of years. These would be very rare objects, and distinguishing them from the normal background of long-period comet arrivals would be extremely difficult. But the search continues, using the growing database of cometary orbits compiled by observatories around the world. Another approach involves looking for disrupted Oort cloud structure. If the flyby significantly perturbed objects in a particular region of the cloud, there might be a measurable asymmetry in the directions from which long-period comets arrive. This would appear as a subtle imbalance in the distribution of cometary aphelia, the most distant points of their orbits, with a slight excess pointing toward the direction of the encounter. Such an asymmetry would be exceedingly difficult to detect with current data, because the sample of well-characterized long-period comet orbits is small and observationally biased. But future surveys, including those conducted by the Vera C. Rubin Observatory in Chile, will dramatically increase the number of known long-period comet orbits and may reveal such signatures. The temporal evolution of the perturbation also merits attention. The velocity impulses delivered by Scholz to Oort cloud objects were not all identical in magnitude or direction. Objects closer to the star's trajectory received larger impulses than those farther away. Objects on the approaching side of the star received impulses in different directions than those on the receding side. This spatial variation in the impulse creates a wave of perturbation that propagates through the cloud over time, as objects on different orbits respond at different rates to their altered velocities. The result is that the arrival of perturbed comets in the inner solar system will not be a single sharp event, but a gradual process, stretching over millions of years. The peak of the cometary shower will be broad, not sharp, and its exact timing and intensity will depend on details of the Oort cloud's density profile and velocity distribution that are currently poorly constrained. The fifth thread is perhaps the most profound. It concerns the origin of the Oort cloud itself, and what stellar encounters tell us about the environment in which our solar system was born. Computer simulations of the solar system's early evolution suggest that the Oort cloud was built primarily from icy planetesimals that formed in the region between the orbits of the giant planets and were then ejected outward by gravitational interactions with Jupiter, Saturn, Uranus, and Neptune. These objects were flung to enormous distances, where the tidal forces of the galaxy gradually circularized their orbits, trapping them in the vast spherical shell we now call the Oort cloud. But there is a problem. Simulations show that this ejection process alone cannot account for the full population of the Oort cloud. Too many objects are lost to interstellar space, ejected on hyperbolic trajectories that carry them beyond the Sun's gravitational reach. To explain the observed number of long-period comets, the Oort cloud must contain more objects than the ejection process alone can provide. Where did the extra objects come from? One compelling answer comes from the Sun's birth cluster. The Sun did not form in isolation. It was born roughly 4.6 billion years ago in a cluster of perhaps 1,000 or more stars, all forming from the same giant molecular cloud of gas and dust. In such a densely packed environment, the protoplanetary disks of neighboring stars would have overlapped gravitationally. Objects ejected from one star's disk could have been captured by another. Some of the objects in our Oort cloud may have originally formed around other stars in the Sun's birth cluster, stolen by our Sun's gravity during the chaotic early days when the cluster was still dense enough for such exchanges to occur. This idea, proposed by Harold Leveson, Luke Dones, and others, suggests that the Oort cloud is not purely a product of our own solar system's formation. It is a communal structure assembled from the debris of multiple stellar systems. If this is correct, then some of the comets that grace our skies, the spectacular long-period comets that arrive from the Oort cloud once every few millennia, may contain material that was never part of our solar system at all. They may be fragments from the protoplanetary disks of stars that have long since dispersed into the galaxy, carrying chemical signatures of alien solar systems within their icy cores. This is not science fiction. This is the current scientific understanding of the Oort cloud's origin, supported by detailed numerical simulations and consistent with the observed properties of long-period comets. It means that the boundary between our solar system and the rest of the galaxy has always been more permeable than we imagined. Stars pass through, comets are exchanged, material from one system ends up in another. The solar system is not a fortress, it is a harbour, with ships arriving and departing on timescales that dwarf human history. the question of how many objects were perturbed by Scholz's star remains open. The 36 hyperbolic objects identified in the 2018 study represent only those that have already passed through the inner solar system and been observed by astronomers. The total number of objects perturbed from the Oort cloud could be orders of magnitude larger. Most perturbed objects will never come close enough to Earth to be detected. They will orbit in the vast empty spaces between the planets, invisible and uncounted, for millions of years before being ejected from the solar system or absorbed into the Oort cloud's general population. The composition of these objects is itself a fascinating question. Oort cloud bodies are believed to be composed primarily of water ice, with admixtures of frozen carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. Their surfaces may be darkened by billions of years of exposure to cosmic radiation, which converts surface ices into dark tarry organic compounds called tholins. When one of these objects is perturbed into the inner solar system and approaches the Sun, the solar radiation heats the surface, sublimating the ices and releasing jets of gas and dust that form the comet's characteristic coma and tail. The composition of these outgassing products provides clues about the chemical conditions that prevailed in the outer solar system 4.6 billion years ago when the Oort cloud was being assembled. If the hypothesis that some Oort cloud objects were captured from other stars in the Sun's birth cluster is correct, then some of these comets may contain material that formed in chemically distinct environments. Different stars form from molecular clouds with different isotopic ratios and chemical abundances. A comet that originated around a star with a different carbon to oxygen ratio, for example, might display subtle but detectable chemical differences compared to a comet that formed in our own protoplanetary disk. Identifying these chemical fingerprints in cometary material is a goal of future space missions, including potential sample return missions to long-period comets. The technical challenges of such a mission are immense. Long-period comets move at high velocities relative to the inner solar system, making rendezvous extremely difficult. They are also discovered with relatively short lead times, typically only a few years before their perihelion passage, leaving little time to design and launch a mission. But the scientific payoff would be extraordinary. A sample from an Oort cloud comet would be a fragment of the solar system's deepest past, a piece of the primordial material from which the planets were built, preserved in the cosmic deep freeze for billions of years. There is yet another dimension to the Scholz's star story that merits attention, and it concerns the methodology of discovery itself. The identification of Scholz's star as a former solar system intruder required the intersection of several independent lines of evidence. The WISE infrared survey, ground-based spectroscopic follow-up to measure radial velocity, parallax measurements to determine distance, and computational simulations to trace the star's trajectory backward through time. No single observation or instrument could have made this discovery alone. It required the collaborative effort of multiple observatories, multiple datasets, and multiple analytical techniques. This is increasingly the norm in modern astronomy, where the most significant discoveries emerge not from single dramatic observations, but from the patient synthesis of data from many sources. The Gaia mission, operated by the European Space Agency, exemplifies this approach. Gaia is creating a three-dimensional map of the Milky Way with unprecedented precision, measuring the positions, distances, and velocities of over 1 billion stars. The resulting catalogue is a treasure trove for stellar encounter research, enabling astronomers to trace the trajectories of hundreds of thousands of stars forward and backward in time with remarkable accuracy. The Gaia data has already refined our understanding of Scholz's star's flyby and has dramatically improved predictions for Gliese 710's future encounter. As additional data releases from Gaia become available, we can expect further discoveries of past and future stellar flybys, potentially including encounters that were even closer than Scholz's star. The search for past stellar encounters is not merely an academic exercise. It has practical implications for understanding the long-term evolution of the solar system. If a particularly close or massive stellar encounter occurred in the distant past, it could have perturbed not just the Oort cloud, but the orbits of the outer planets themselves. Simulations have shown that a star passing within a few hundred astronomical units of the Sun could measurably alter the orbit of Neptune, and changes to Neptune's orbit would cascade through the entire outer solar system, affecting the Kuiper belt, the scattered disk, and the inner Oort cloud. While such close encounters are extremely rare, the solar system is old enough that one or more may have occurred over its 4.6 billion year history. Identifying such encounters could help explain some of the unexplained features of the outer solar system's architecture, such as the anomalous orbits of certain trans-Neptunian objects. The deeper truth revealed by Scholz's star is not about one dim red dwarf that passed too close 70,000 years ago. It is about the nature of our cosmic environment and the illusion of stability that pervades our understanding of the solar system. We live in a system that appears stable. The planets trace their orbits with clockwork precision, the seasons cycle, the tides rise and fall. On human timescales, the solar system seems eternal and unchanging, a mechanism running with perfect reliability since before life began. But this appearance of stability is, in large part, a trick of timescale. On timescales of millions and billions of years, the solar system is anything but stable. It is buffeted by external forces, shaped by passing stars, perturbed by galactic tides, and occasionally disrupted by encounters that can reshape entire orbital architectures. Let that sink in. The Sun has orbited the center of the Milky Way roughly 20 times since the solar system formed. Each orbit takes approximately 225 million years. Over the course of those 20 galactic orbits, the Sun has passed through spiral arms, traversed regions of high and low stellar density, and encountered countless other stars. Some of those encounters were distant and inconsequential. Others were close enough to send cometary showers into the inner solar system, and a few, perhaps, were close enough to affect the orbits of the outer planets themselves. The Oort cloud serves as a kind of cosmic memory, a record of these encounters etched into the orbits of its trillions of members. Each passing star leaves a fingerprint, a subtle distortion in the orbital distribution of nearby Oort cloud objects. The 2018 study by De La Fuente Marcos and colleagues identified one such fingerprint, a clustering of hyperbolic orbits pointing toward the constellation Gemini, consistent with the Scholz's star flyby. But there are other fingerprints, other clusterings, other signatures of encounters that we have not yet identified or attributed to specific stars. Let that sink in. The comets that occasionally light up our night sky, the spectacular apparitions that have inspired awe and fear throughout human history, may be the direct consequences of stellar encounters that occurred millions of years ago. A star passes through the Oort cloud. It nudges a few thousand icy bodies onto new trajectories. 2 million years later, those bodies arrive in the inner solar system as comets. We see them, name them, photograph them, study them. And then they pass, either falling into the Sun or swinging back out to the Oort cloud, carrying with them the kinetic memory of an encounter that predates the existence of our species. This is the cosmic conveyor belt that connects the distant Oort cloud to the night sky above our heads. It runs continuously, delivering a slow but steady stream of comets from the outermost reaches of the solar system to its innermost regions. The rate of delivery is modulated by stellar encounters, galactic tides, and the gravitational architecture of the giant planets. And it has been running for 4.6 billion years, since before the first single-celled organisms appeared on Earth. The implications for Earth are worth considering carefully. The vast majority of comets that enter the inner solar system do not strike Earth. The inner solar system is mostly empty space, and the probability of a comet hitting any particular planet is extremely small. But over geological time, the cumulative probability is not negligible. Earth has been struck by comets in the past. The late heavy bombardment, a period of intense cometary and asteroidal bombardment roughly 4 billion years ago, is thought to have delivered much of Earth's water and organic material. More recent cometary impacts may have contributed to mass extinction events. Though the evidence for this remains debated, the risk posed by Scholz's star's flyby is, by all credible scientific analyses, minimal. The perturbation was weak. The comets it dislodged, if any, will not arrive for nearly 2 million years. And when they do arrive, most will miss the inner planets entirely. As Eric Mamajek himself put it, he is not losing sleep over comets perturbed by Scholz's star. There are many more immediate concerns on Earth, and most are fixable. But the flyby of Gliese 710, expected in approximately 1.29 million years, is a different matter. That encounter will be the strongest disrupting event in the known past and future history of the solar system, based on current trajectory data. The cometary shower it triggers will last for millions of years and will significantly increase the flux of long-period comets in the inner solar system. Whether any of those comets will strike Earth is unknowable at this point, but the probability of impact will be elevated, and it will remain elevated for geological timescales. This is not science fiction. This is the output of sophisticated numerical simulations published in peer-reviewed astronomical journals. Gliese 710 is real. Its trajectory is well measured. Its closest approach distance, refined using data from the Gaia Space Telescope, is known to within about 500 astronomical units. And its arrival, while distant by human standards, is certain by astronomical ones. The concept of a cometary shower has a specific technical meaning that is worth clarifying. In normal times, long-period comets arrive in the inner solar system at a roughly constant rate, a few per year bright enough to be observed from Earth. This baseline rate is maintained by the continuous action of the galactic tide and the occasional perturbation from relatively distant stellar encounters. A cometary shower occurs when a single event, such as a close stellar flyby, sends a large pulse of comets inward from the Oort cloud. This pulse travels inward over millions of years, arriving in the inner solar system as a temporary increase in the cometary flux. The shower begins gradually, peaks, and then slowly subsides as the perturbed population spreads out and is absorbed into the background. The cometary shower predicted from the Gliese 710 encounter is expected to begin arriving roughly 1 to 2 million years after the closest approach, peak in intensity at around 2 to 3 million years, and persist at elevated levels for approximately 4 million years total. The spatial distribution of the shower will not be uniform. Early arriving comets will be concentrated near the antiperihelion direction, the point in the sky directly opposite the direction from which Gliese 710 approached. Over time, the distribution will spread, eventually becoming nearly isotropic. The risk to Earth from such a shower is real, but should be placed in context. Even during a cometary shower, the probability of a specific comet striking Earth in any given year is extremely small. Comets are widely spaced, the inner solar system is mostly empty, and Earth is a tiny target. The primary risk is not from a single catastrophic impact, but from the cumulative increase in impact probability over millions of years. A 50% increase in cometary flux sustained over 4 million years translates to a meaningful increase in the total number of expected impacts. But even with this increase, the probability of a specific civilization-ending cometary impact during the shower remains very low. The deeper concern is not about any single event, but about our relationship with time and probability. We tend to think of risks as either present or absent as binary states, but cosmic risks are probabilistic and continuous. The probability of a cometary impact is never zero. It fluctuates with the cometary flux, which in turn fluctuates with the rate and intensity of stellar encounters and galactic tidal perturbations. We live within a probability field, bathed in a low but non-zero level of cosmic risk at all times. Stellar encounters like Scholz's star and Gliese 710 modulate this risk, turning the dial up or down by small increments. And the vast majority of these modulations, the ones from distant or small stars, are so slight that we cannot detect them. We feel only the cumulative effect, the steady background rate of cometary arrivals, without knowing which specific encounter set each one in motion. This probabilistic relationship between stellar encounters and cometary flux creates a kind of cosmic uncertainty principle for long-term planetary defense. We can predict the broad outlines of future cometary showers using the trajectories of known nearby stars, but we cannot predict the specific comets that will arrive, their sizes, their compositions, or their exact trajectories. The only preparation that makes sense is general purpose readiness, the ability to detect and track incoming comets, the technology to deflect or destroy them if necessary, and the institutional capacity to make decisions on the timescales required. These are the same capabilities needed for asteroid defense, and they are equally incomplete. The story of Scholz's star, viewed from this perspective, is not primarily about a single historic event. It is about the recognition that the solar system exists within a dynamic, unpredictable environment, and that the threats from that environment are ongoing, diffuse, and essentially permanent. There will never be a time when we can declare the sky safe and stop watching. The stars will keep passing, the comets will keep falling, and the only defense is awareness, preparedness, and the patient, ongoing work of understanding the cosmos well enough to see what is coming before it arrives. The question of detection also extends to the brown dwarf component of the Scholz's star system. Brown dwarfs are among the most elusive objects in the galaxy. They emit most of their energy in the infrared, at wavelengths that are largely absorbed by Earth's atmosphere. Ground-based detection requires specialized instruments operating at high altitude, dry sites, or space-based telescopes like WISE. The population of brown dwarfs in the solar neighborhood is still being catalogued, and new discoveries continue to be announced regularly. It is possible that there are undiscovered brown dwarfs or very low-mass stars even closer to the Sun than Scholz's star, hidden by their extreme faintness and unfavorable geometries. The Gaia mission, while primarily designed for optical wavelengths, is also contributing to the census of nearby low-mass objects. But a complete survey of the solar neighborhood down to the lowest masses will require next-generation infrared space telescopes. The relationship between Scholz's star and the broader population of nearby stellar systems also raises questions about the frequency of close encounters in the deep past. The solar neighborhood has changed dramatically over the Sun's 4.6 billion-year lifetime. Stars that are now far away were once close. Stars that are now close will someday be far away. The Sun's orbit through the galaxy carries it through different stellar populations at different times. During passages through the galaxy's spiral arms, where stellar density is higher, close encounters would have been more frequent. During passages through the interarm regions, encounters would have been rarer. The net effect, averaged over the Sun's lifetime, is a continuous but fluctuating rate of Oort cloud perturbation that has shaped the cloud structure and regulated the flow of comets into the inner solar system throughout the entire history of the solar system. This realization places every comet we have ever observed in a new light. Comet Halley, which returns to the inner solar system every 75 to 79 years, is a short-period comet that has been captured from the Oort cloud into a stable orbit among the planets. But it was not always a short-period comet. At some point in the past, perhaps millions of years ago, it was an Oort cloud object on a nearly circular orbit at vast distance from the Sun. Something perturbed it, a passing star, the galactic tide, a giant molecular cloud, and sent it falling inward. It passed the giant planets, was captured into a shorter orbit by their gravity, and began its repeated visits to the inner solar system. Every return diminishes it slightly, as solar heating strips away layers of ice and dust. Eventually, perhaps in a few 100,000 years, it will be exhausted, reduced to a dark, inert remnant that no longer produces a visible coma or tail. It will become an extinct comet, a dead husk drifting among the planets, invisible and forgotten. This life cycle connects every comet to the forces that shaped the Oort cloud. Every comet is a message from the outer solar system, a fragment of the primordial material that built the planets, dislodged from its ancient home by forces that operate across the galaxy. When we observe a comet, we are observing the end point of a chain of events that began millions of years ago, in the gravitational wake of a passing star or the subtle tide of the Milky Way. Scholz's star is one link in that chain. The next link, from Gliese 710, is already being forged. The solar system is not a closed box. It never has been. It is an open system, continuously interacting with its galactic environment. Stars pass through. Comets are exchanged. Gravitational perturbations ripple through the Oort cloud, and eventually reach the inner planets as new cometary arrivals. The boundaries of the solar system, which we draw on diagrams as neat circles and spheres, are in reality porous, permeable, and subject to constant revision by the gravitational forces of the galaxy. There is a final thread that connects the story of Scholz's star to the broadest questions in astronomy. The passage of a star through the Oort cloud is in essence a gravitational experiment performed by the cosmos itself. The star applies a known force, calculable from its mass, velocity, and trajectory, to a known population of objects, the Oort cloud. The response of those objects, their altered orbits, their redistribution, their eventual arrival as comets in the inner solar system, is the outcome of the experiment. By observing that outcome, astronomers can learn about the structure and composition of the Oort cloud itself, a structure that has never been directly observed, but whose existence is inferred from the very comets it produces. This is a kind of cosmic tomography, using stellar flybys as probes to image the internal structure of the cloud. Each flyby perturbs a different region of the cloud from a different direction with a different intensity. The resulting cometary signals, arriving in the inner solar system over the subsequent millions of years, carry information about the density, distribution, and dynamics of the cloud in the region that was perturbed. By accumulating data from multiple flyby signals over geological time, it may eventually be possible to build a three-dimensional map of the Oort cloud, not from direct observation, but from the cometary echoes of stellar encounters. This idea is speculative, but it is grounded in solid physics. The relationship between the perturbation, which can be calculated from the known trajectory of the passing star, and the response, which can be observed in the distribution of incoming comets, is governed by well-understood gravitational dynamics. The challenge lies in separating the signal from the noise, distinguishing comets perturbed by a specific stellar encounter from the background of comets produced by the continuous action of galactic tides and other perturbations. But with enough data, over long enough timescales, the signal should be detectable. This prospect gives the story of Scholz's star a forward-looking dimension that extends far beyond the immediate question of whether the flyby endangered Earth. It suggests that stellar encounters are not merely hazards to be endured, but opportunities to learn, windows into the structure of a part of the solar system that is otherwise inaccessible to direct observation. Every star that passes through the Oort cloud is, in a sense, a probe that we did not launch, gathering data that we did not request, delivering results that we will not see for millions of years. The cosmos is performing experiments on our behalf, writing the results in the language of cometary orbits, waiting for someone to read them. Scholz's star taught us this lesson. It showed us that our solar system is not an island, but a peninsula, connected to the wider galaxy by bridges of gravity and time. It showed us that stars can enter our domain without detection, leaving behind gravitational signatures that take millions of years to manifest. And it showed us that the history of our solar system is not a story of splendid isolation, but of continuous interaction, a story written in the orbits of comets and the trajectories of passing stars, a story that stretches back to the sun's birth in a crowded stellar nursery and forward to the inevitable close passage of Gliese 710 and the cometary shower that will follow. The cometary shower, triggered by Gliese 710, deserves closer examination because the numbers involved are striking. Computer simulations predict that the encounter will deflect a significant number of Oort cloud objects onto new trajectories. The density of the resulting cometary showers is estimated at roughly 10 new comets per year entering the observable solar system, concentrated initially near the anti-perihelion direction. This shower will persist for 3 to 4 million years, gradually dispersing across the sky as the perturbed orbits spread out. 10 comets per year may not sound like much. The current baseline rate of long-period comet arrivals in the inner solar system is roughly 1 to 2 per year that are bright enough to be observed from Earth. A tenfold increase would be noticeable, but not catastrophic. Most of these comets would pass through the inner solar system without approaching Earth closely. But over millions of years, the cumulative probability of a cometary impact on Earth would be elevated. The precise degree of elevation is difficult to calculate because it depends on the size distribution of the perturbed objects, their orbital inclinations, and the gravitational filtering effects of the giant planets. But a 50% increase in long-period comet flux, as some estimates suggest, translates to a meaningful increase in impact risk over geological timescales. To put this in perspective, consider the current impact risk from long-period comets. The annual probability of a civilization-threatening cometary impact, defined as an impact from an object larger than 1 kilometer in diameter, is estimated at roughly 1 in several million. A 50% increase in comet flux raises this to roughly 1.5 in several million. Over the 3 to 4 million year duration of the shower, the cumulative probability becomes significant, perhaps several percent. This is not a catastrophic increase, but it is not negligible either. The response of the scientific community to the Scholz's star discovery and the Gliese 710 prediction has been measured and appropriately cautious. Eric Mamajek himself emphasized that there are many more immediate concerns on Earth, and that the risks from cometary showers triggered by stellar encounters are small compared to other existential threats. But the research has had a lasting impact on our understanding of the solar system's long-term, dynamical environment. It has demonstrated that the Oort cloud is not a static, unchanging structure, but a dynamic system continuously shaped by external forces. And it has highlighted the importance of continued investment in stellar astrometry, cometary science, and planetary defense. The story also illuminates a broader philosophical point about the nature of time and human awareness. 70,000 years ago, when Scholz's star passed through the Oort cloud, modern humans were just beginning to develop the cognitive and cultural capabilities that would eventually lead to language, art, science, and technology. The stone tools they were crafting were 1,000,000 years old in design. The cave paintings that would later be created in Lascaux and Altamira were still 30,000 years in the future. Agriculture was 60,000 years away. Writing was 65,000 years away. The telescope was 69,700 years away. And the infrared space telescope that would eventually reveal the star's passage was 69,990 years away. In the span of time between the flyby and its discovery, our species transformed itself from a small population of hunter-gatherers, struggling for survival on the African savanna, into a global civilization capable of launching instruments into space, mapping the positions of 1 billion stars, and reconstructing events that occurred before the dawn of recorded history. The distance between those two moments, 70,000 years, is vast by human standards but trivially short by cosmic ones. The Oort cloud objects, nudged by Scholz's star, have barely begun their journey inward. They have covered perhaps 3 to 4% of the distance from the outer cloud to the inner solar system. They will not arrive for another 2 million years. And 2 million years from now, who will be here to see them? This question has no answer. It is a question that hangs in the air like the star itself once hung in the sky, visible only to those who know how to look. But the asking of it, the very fact that we can ask it, is itself a testament to the extraordinary reach of human understanding. We are small, brief, fragile creatures on a small, brief, fragile world. And yet we can look backward 70,000 years and reconstruct the passage of a star through the edge of our solar system. We can look forward 1.3 million years and predict the arrival of another. We can count the trillions of icy bodies in the Oort cloud, estimate their orbits, and calculate the probability of any one of them striking our planet in the distant future. These are not small achievements. They are the achievements of a species that has learned to see beyond the limits of its own senses, beyond the horizon of its own lifespan, beyond the boundary of its own tiny world. What does it mean that a star passed through our solar system and no one noticed? What does it mean for our understanding of where we are, what surrounds us, and how vulnerable we truly are? The first implication is epistemic. It concerns the limits of our knowledge. Scholz's star was 22 light-years away and was not discovered until 2013. It had been there, presumably, for billions of years. It had been nearby, by cosmic standards, for thousands of years. And yet it took the development of space-based infrared astronomy, advanced proper motion surveys, and the meticulous work of a single astronomer to bring it to our attention. If a star this close could escape detection for so long, then the catalogue of nearby stellar objects is less complete than we might assume. There may be other dim stars, brown dwarfs, or even rogue planets drifting through the solar neighborhood that we have not yet found. Some of them may be on trajectories that will bring them through the Oort cloud in the future, and we will not know about them until we look. This is a reminder that the universe does not reveal itself voluntarily. It must be interrogated. It must be probed and measured and analyzed with tools of ever-increasing precision. Every new telescope, every new survey, every new dataset reveals objects and phenomena that were previously invisible. The history of astronomy is a history of expanding awareness, of the slow peeling back of ignorance to reveal a cosmos that is always larger, always more complex, and always more dynamic than we previously understood. The second implication is temporal. It concerns the mismatch between human timescales and cosmic ones. Scholz's star passed through the Oort cloud 70,000 years ago. The comets it may have perturbed will not arrive for nearly 2 million years. Gliese 710 will arrive in 1.3 million years and trigger a cometary shower lasting several million years more. These timescales are incomprehensible to human intuition. We struggle to plan for the next decade, let alone the next million years. Our institutions, our governments, our civilizations last centuries at most. The longest-lived human structures are a few thousand years old. Against the time scales of stellar encounters and cometary showers, human civilization is a momentary flicker, and yet the processes are real. They are happening now. The comets perturbed by Scholz's star are moving through the Oort cloud at this very moment, slowly spiraling inward on trajectories that will carry them past the giant planets and into the inner solar system long after every human alive today has been forgotten. Gliese 710 is approaching at roughly 14.5 kilometers per second, closing the gap between us by about 458 million kilometers every year. These are not future possibilities. They are present realities unfolding on timescales too long for us to perceive, but too certain for us to ignore. There is a philosophical dimension here that deserves acknowledgement. The realization that our solar system is not isolated, that stars pass through regularly, that the comets we see may have been knocked loose by encounters millions of years in the past, challenges a deeply held assumption about our place in the cosmos. We tend to think of the solar system as ours, our sun, our planets, our space. But the Oort cloud, the outermost boundary of that space, is a shared resource, shaped by galactic forces, populated partly by material stolen from other stars, and continuously modified by passing neighbors. The solar system is less like a walled garden and more like an open field, part of a larger landscape that extends in all directions to the stars. Consider the scale of this landscape. The Sun's nearest stellar neighbors, the three stars of the Alpha Centauri system, are approximately 4.2 light-years away. But light-years are deceptive units. 4.2 light-years is roughly 265,000 astronomical units. The outer edge of the Oort cloud extends to approximately 100,000 astronomical units. This means the Oort cloud reaches roughly one-third of the way to Alpha Centauri. If Alpha Centauri has its own Oort cloud of similar dimensions, the two clouds may nearly overlap. The space between the stars, which appears so empty in popular depictions, may actually be threaded with icy debris from multiple stellar systems, a vast, diffuse web of frozen material connecting the stars like a cosmic circulatory system. This idea is speculative, but it is consistent with what we know about the density of interstellar space and the mechanics of cometary ejection. It suggests that the solar system is not merely visited by passing stars, but is embedded within a network of gravitational and material connections that links it to its neighbors. The comets we see may have histories that span multiple stellar systems. The water on Earth may have arrived partly on comets that originated around other stars. The raw materials of life may have been assembled from ingredients gathered across a region of the galaxy far larger than the solar system itself. We are, in a very real sense, citizens of the galaxy, not just inhabitants of the solar system. The boundary between the two has always been thinner than we thought, and Scholz's star, That dim, unassuming red dwarf that crept through our Oort cloud while our ancestors sat around campfires and stared at the sky, is the proof. There is one more thing to consider. The very concept of the solar system's boundary is itself an approximation. The Oort cloud blends into interstellar space without a sharp edge. The sun's gravitational influence fades gradually, never quite reaching zero. At some point, the galaxy's gravity dominates, but the transition is smooth, not sudden. This means the solar system does not end. It merely becomes less and less solar and more galactic. And in that transition zone, the Oort cloud, the comets within it respond to both influences simultaneously, pulled by the sun and pushed by the galaxy, and occasionally kicked by a passing star. They are objects of the boundary, belonging fully to neither realm, perpetual wanderers at the margin of the sun's domain. Scholz star passed through that margin. Gliese 710 will pass through it more deeply. Others have passed through before, unnamed and unrecorded. And still others will come, in the millions and billions of years that stretch ahead, each one a reminder that the cosmos does not respect the lines we draw on our maps. The question of whether stellar encounters have played a role in Earth's biological history is one of the most tantalizing in all of science. Several researchers have noted apparent periodicities in the record of mass extinctions, impact crater formation, and cometary activity, and have speculated that these periodicities might be linked to the sun's oscillation through the galactic plane or to periodic encounters with stars or giant molecular clouds. The most famous of these hypotheses is the nemesis theory, proposed in 1984 by Richard Muller and others, which suggested that the sun has a dim, distant companion star on an elongated orbit that periodically passes through the Oort cloud and triggers cometary showers every 26 million years or so. This companion, dubbed Nemesis, has never been found, and the hypothesis has largely fallen out of favour. But the underlying idea that external perturbations can influence the cometary flux, and, by extension, the impact rate on Earth remains scientifically viable. The connection between stellar encounters and cometary showers is well established in theory and increasingly supported by observation. The clustering of hyperbolic orbits identified in the 2018 study is one piece of evidence. The predicted cometary shower from Gliese 710 is another. And the general theory of Oort cloud dynamics, developed over decades by researchers including Jan Oort, Jack Hills, Nathan Kaib, and many others, provides a robust framework for understanding how external perturbations translate into changes in cometary flux. What remains uncertain is whether these changes in cometary flux have historically resulted in increased impact rates on Earth. The crater record is incomplete, particularly for older craters that have been eroded or subducted. The attribution of specific mass extinction event to cometary impacts as opposed to volcanic activity, climate change, or other causes is difficult and often contested, and the statistical analysis of periodicities in the extinction and cratering records is fraught with methodological challenges. But the possibility is there. It is a thread that connects the passage of stars through the Oort cloud to the history of life on Earth, linking the grandest scales of galactic dynamics to the most intimate details of biological evolution. If a star that passed through the Oort cloud 5 million years ago nudged a comet that struck Earth 3 million years later, triggering an environmental catastrophe that drove certain species to extinction and opened ecological niches for others, then the course of evolution itself was shaped, in part, by the motion of a star through interstellar space. The connections are attenuated and uncertain, but they are possible, and they remind us that life on Earth does not exist in a vacuum. It exists within a galaxy, subject to forces that operate on timescales far longer than any individual species and across distances far greater than any planet. The philosophical weight of this realization is considerable. It suggests that the history of life on Earth is not merely a product of local conditions, of climate and geology and biochemistry, but is also influenced by the broader galactic environment, the stars that pass near the sun, the comets they dislodge, the impacts those comets occasionally produce. All of these are part of the story of life, and that story extends beyond the boundaries of the solar system, into the vast, dynamic, interconnected web of the Milky Way galaxy. Somewhere out there, right now, at this very moment, trillions of icy bodies are drifting through the darkness at the edge of the sun's gravitational reach. They are small, cold, and ancient. Most of them have orbited the sun since before the first life appeared on Earth. They have witnessed nothing, recorded nothing, felt nothing. They simply exist, in the silence between the stars, following the slow curves of orbits that take millions of years to complete. 70,000 years ago, a dim red star and its even dimmer companion passed among them. The star's gravity tugged at some of them, gently, imperceptibly, altering their trajectories by fractions of a meter per second. Those nudged bodies began new journeys, new orbits, new falls toward the distant sun. They are still falling. They will continue to fall for nearly 2 million more years. And when they arrive, they will appear in our sky as comets, bright visitors from the edge of the solar system, carrying within their icy cores the chemical memory of the solar system's birth and the gravitational memory of a star that passed too close. No one alive today will see those comets. No civilization that currently exists may endure long enough to observe them. But they are coming. They are already on their way, as certain as gravity, as patient as time. Scholz's star is now 22 light-years away, receding from us at 83 kilometers per second. It will never return. It has no interest in us, no awareness of us, no knowledge that it once passed through the outermost reaches of a small star's domain, and was noticed, briefly, by a species that had only just learned to look up. It is simply a star, an unremarkable M-class red dwarf with a brown dwarf companion, following its own orbit through the Milky Way, obeying the same laws of physics that govern every other speck of matter in the universe. But we noticed it. That matters. We noticed it because one astronomer, Ralph Dieter Scholz, was careful enough to spot a faint anomaly in a vast dataset. We noticed it because another astronomer, Eric Mamajek, was curious enough to trace its trajectory backward in time and realize what it meant. We noticed it because centuries of scientific progress had given us the tools to see what was invisible and measure what was imperceptible. A star passed through our solar system, and we figured it out. 70,000 years later, using instruments that would have seemed like magic to the humans who lived through the event, we reconstructed what happened and understood its significance. That is the power and the fragility of our situation. We are the first species on this planet capable of knowing that stars pass through the solar system. The dinosaurs could not have known. The trilobites could not have known. For 4.6 billion years, stars have passed through the Oort cloud, perturbing comets, reshaping orbits, occasionally contributing to the bombardment of the inner planets. And for 4.6 billion years, no one here knew it was happening. Now we know, and knowing changes everything, even if the events themselves are too distant and too slow to affect us directly. Knowing that Scholz's star passed through the Oort cloud places our solar system in a galactic context. It connects us to the stars around us. It reminds us that the sun is moving through a dynamic environment, not floating in a void, and it alerts us to future encounters, like Gliese 710, that will be far more consequential. The night sky, to most people, is a canvas of fixed lights, beautiful but static, eternal and unchanging. But it is not. The stars are moving. They have always been moving. Some are coming closer. Some are moving away. And once in a very long while, one of them comes close enough to enter the outermost rooms of our celestial home, to brush against the frozen debris at the edge of the sun's domain, and to set in motion a chain of events that takes millions of years to unfold. We are temporary witnesses to a process that is almost incomprehensibly slow and incomprehensibly vast. Stars drift, comets fall, planets orbit, and somewhere in the space between the stars, icy fragments from the birth of the solar system are slowly, patiently making their way toward a sun that has no idea they are coming. Scholz's star has already passed. Gliese 710 is already approaching. And in the Oort cloud, in the deep, cold silence at the edge of the solar system, trillions of ancient objects continue their slow, patient orbits, waiting for the next gravitational visitor to nudge them loose and send them falling toward the distant light of home. The cosmos does not hurry. It does not need to. It has all the time there is. The silence of the Oort cloud is not the silence of emptiness, it is the silence of patience. 2 trillion objects, each one a frozen world no larger than a mountain, orbiting the sun at distances that light itself takes months to cross. They have been there for billions of years. They will remain for billions more. And every 100,000 years or so, a star will pass among them, close enough to nudge a few loose, to send them drifting inward on journeys that will take millions of years to complete. This is the rhythm of the outer solar system. It is slow and vast, and utterly indifferent to the brief, bright civilizations that flicker on the surface of the third planet from the sun. But those civilizations, brief as they are, have achieved something remarkable. They have looked outward, past the planets, past the Kuiper belt, past the heliopause, all the way to the Oort cloud's frozen edge, and they have understood. They have understood that stars pass by. They have understood that comets fall. They have understood that the solar system is not a fortress but a harbour, open to the galaxy, connected to the stars, subject to forces that no wall can keep out. This understanding is young. It is barely a century old, in its modern scientific form. Jan Oort proposed his cloud in 1950. The first stellar flyby was identified in 2015. The first detailed prediction of a future cometary shower was published in 2016. In the vast sweep of human history, these discoveries are moments ago. And in the vast sweep of cosmic time, the events they describe are still unfolding, still rippling through the outer solar system, still setting in motion chains of cause and effect that will not resolve for millions of years. We stand at a peculiar moment in the history of our species. We are old enough to have developed the tools to understand our cosmic environment, but young enough that most of the threats we have identified lie far in the future. Scholz's star has already passed. Its cometary consequences are millions of years away. Gliese 710 is more than 1,000,000 years from its closest approach. We have time. But time, as the Oort cloud teaches us, is not the same as safety. The objects are already in motion, the trajectories are already set. The future is already falling toward us, slowly, patiently, with the certainty of gravity and the indifference of the void. In the end, the story of Scholz's star is not about a single star or a single flyby. It is about the relationship between the solar system and the galaxy that contains it. It is about the porosity of boundaries that we once thought were absolute. It is about the connections between events separated by millions of years and trillions of kilometers. And it is about us, a species that learned to trace these connections, to read the signatures of ancient encounters in the orbits of present-day objects, and to look forward into a future shaped by forces that were set in motion before we existed. The sky is dark, the stars are moving, and somewhere at the edge of the sun's domain, in the cold, patient silence of the Oort cloud, trillions of ancient objects continue their long, slow orbits, waiting for the next gentle nudge from a passing star. They have waited before, they will wait again. The cosmos is nothing if not patient.